Today we're going to take a look at the binomial distribution. The binomial distribution can be used to model a sequence of independent trials. So we saw the Bernoulli distribution, which models a single trial. The binomial distribution can model a sequence of trials, but each of the trials must be independent. So the probability of, for example, if in case of say coin flips, if we flip a coin 10 times, then the probability of getting ahead the second time you flip is the same as the probability of getting ahead the first time you flip, which is the same as the probability of getting ahead the 10th time you flip. So we're going to use the binomial distribution here to model a sequence of 10 coin flips. As before, success is represented by value 1 and failure by value 0, and we again consider obtaining a head as a success. So we create our sequence. What we're going to do is we're going to do 10 trials, and then we use the dbinom function. We pass it our trial vector, and we set the parameters of the distribution are the number of trials, in this case 10, and the probability of success, which we're going to say is a half because we're dealing with a fair coin. So if we run this and we plot this, we get our little graph. So let's just do it. So for example, we see that the probability of getting no heads is just above 0, so it's possible but unlikely. The probability of getting say 2 heads is just under 5%. The probability of getting 5 heads is 0.25, which is interestingly the most likely, which is what we would expect. Since the probability of a head is a half, we would expect that when we flip the coin 10 times, 5 of those times will be heads. And so we see that the binomial distribution has a very interesting shape. If we join the dots together, we would get a bell curve. And for those of you who know statistics, you understand what that means. What's interesting is that we will look at the implications of this shape in a future video. But for now, let's try and work out some probabilities. So for example, we want to find the probability of obtaining no heads. So that means that we pass 0, is dbinom 0. Again, 10 is our parameters, and probabilities 5. So by the way, this here is, if you know the probability mass function for binomial distribution, it's equal to 10 choose 10 times 0.5 to 0, because that's the number of heads, times 0.5 to the 10, which is the number of tails, because the probability of getting, can you see, the tails is 0.5. So what we're saying is the number of different ways we can get no heads and 10 tails, that's the probability of obtaining no heads, which of course there's only one, but when we run this, we get 0.00097. So it's less than 1%, so it's quite unlikely. In fact, it's more like a tenth of a percent. So it's quite unlikely, but possible. So let's find the probability of obtaining 5 heads. So in 10 trials, we do that, we run this, and we get 0.246, okay, which is about 0.25, which, as we saw from the graph. So that's the most likely. That's what we would possibility, because, and of course it's most likely, and it's also the it's I forgot what I was going to say. Anyway, let's continue. Probability of getting at least 1 head. Okay, we run that. Now, this is a little interesting because now we're using the binomial function, because we want to know what the probability of getting at least 1 head is. Probability of getting at least 1 head is the probability of getting no heads, plus the probability of getting 1 head, the probability of getting 2 heads. and so on and so forth. Okay, sorry, it's not. Let me start again. Probability of obtaining at least one head, probability of getting only one head, plus the probability of getting only two heads, plus the probability of getting only three heads, and so on and so forth. So we're going to use the p-binomial function, which will give us, instead of, we would have to, if we use d binomial, we'd have to add those individual probabilities together. But p-binomial allows us to do it in one line. So when we run that, we see 0.01. So we've got a 1% chance, roughly, of getting at least one head, which is interesting. And finally, we can perform the 10 flip experiment 5 times. So let's perform this experiment 5 times using the R binomial function. So we're doing it 5 times. Let's see what happens. I run that. Okay, so this is what happened. The first time we got 6 heads, 6 out of 10 heads. Then we did another 10 flips, and 5 out of 10 were heads. Then we did another 10, and 4 out of 10 were heads. We did another 10, and 3 out of 10 were heads. We did another 10, and 5 out of 10 were heads. So that's pretty interesting, because that's just one possibility that could happen. So as an exercise, I would recommend that you use the binomial distribution to model 10 flips of a biased coin. So a biased coin, the probability of getting a head is not the same as getting a tail. So if you try using the binomial distribution to model that and see what you get. Until then, I'll see you next time.